This is a video demonstration for task 2.2. This was focused on the core concept in algorithm and complexity, including time and space analysis, sorting algorithm, and symptomatic notation. It's designed to assist the understanding of efficiency and analyze then how to apply big theta and big omega notation in both theory and code-based example. This task consists of four sections: understanding intersource, the time complexity of operation on a custom generic structure, and here true false justification, and lastly uh, symptomatic analysis of code snipped. So let's go to my answer sheet. In the first question, I described intersort as a hybrid sorting algorithm that combine the quicksort, heap sort, and insert sort to addictively manage the performance. It begin with the quicksort for speed, switch to heap sort to avoid the quicksort worst case scenario of big of n squared, big of n squared. Use insertion sort for small and or nearly sorted array, and I clarify that intersort is unstable since it doesn't preserve the relative order of equal elements. For the time complexity, I highlight that intersort maintain big of n log n for best average and worst case thanks to its smart switching strategy. And in question 3, here I evaluate the time complexity for operation like add, insert, remove, clear, index of, and so of both vector class and .NET list. And in my analysis, show the both structure have identical time complexity for all major operations. For example, uh, this add operation is typically big O of 1 but can be big O of n when resizing occur, and this insert operation and remove at are big O of n due to the need of shift element, and also uh, count and capacity access is big O of 1. A method like contain and index of are the big O of n due to linear scanning. This confirms that the performance characteristics of my custom vector implementation are consistent with the behaviors list in the .NET framework. In here, uh, I review and marked each as incorrect and with justification. Uh, A section I mark this is incorrect because the statement will claim that n big of n the algorithm always run slower than the big O of log n algorithm. While this may be true for the large n for a small input, and the big O of n cube algorithm might actually finish faster. Complexity describes the growth trend and actual execute time. And in B section, this also correct because the bubble sort perform the optimally when the input is already sorted. In this best case scenario, is only make one pass without any swap, resulting in time complexity of big O of n. And here in C section is also correct. Inserts, insertion sort has a worst case complexity of big O of n squared when the input is stored in the reverse order because every element has to be shifted into a position. And the D section also correct selection because selection sort is an in place sorting algorithm that only need a constant amount of extra memory. And is also correct. This because insertion sort perform all the sorting within the array itself and use minimal extra memory. And f is also correct because a fixed value like 2 plus 2 equal 4 independent of input size n and its complexity is big O of 1, and D is also correct. This in this expression n cube plus 106n, the dominant term in n cube, therefore the complexity in big O of n cube. And also the exception is incorrect because the claim that big O of n log n grows slower than big O n is false. For larger n log n grows faster than the linear time, so the statement doesn't hold. And section also correct. In symptomatic term, log n is strictly smaller than n, and J is also correct. Here I mark the statement as a correct because the consists like 2 to the power 100 doesn't grow with the input size. So even though it's the largest number, its growth rate is still that big theta 1, or it can be compared to big theta log n when placed in that context. K marks is correct since the n log n grows faster than n, it's at least in omega n, which represent the lower bound of on performance. And this L is incorrect. This term because because the n to the power the n growth much faster than n, so it cannot be big of n. And this one is also incorrect because the factorial growth and factorial growth is significantly faster than the polynomial growth like big O of n squared, so it can't be said that n factorial equal to big O of n. So all through these all true and false question, I applied key symptomatic principle to evaluate algorithm behavior, and this part of the task confirm my understanding of the difference between growth rate and the actual execution time, and how sorting algorithm behave in best and worst cases, the meaning and the power use of notation like big O, big theta, and big omega, and little o. Then let's move to the question 4. In here I analyze the three different code snip and explain the best case and worst case complexities. So in 4.1, the best case number of big O of n when the flag is false and the inner loop doesn't run. The worst case is big O of n squared when the flag is always true, causing the nested loop execution. And the 4.2, the both best and worst case big O of n, the two loops are independent, so complexity doesn't compound even if the run it is still linear. 4.3, the best and worst case is the big O of n squared. Even in the best case, the comparison is still occur. In the worst case, it performs the maximum number of comparison and swap. These cases require not just justifying the nesting and but also understanding how condition impact runtime behavior. So this is the end of my demonstration. Thank you.